In this video, we will introduce our paper, Reducing Class-Wise Confusion for Incremental Learning with Disentangled Manifolds. Class incremental learning aims to enable models to continuously learn new classes without forgetting old ones. A promising direction is to learn and use prototypes of classes during incremental learning phase. Existing prototype-based methods cannot effectively classify samples with unsatisfied discriminative representations. As observed in figure on the left, Class 7 forms two distinct clusters in the feature space, while the prototype lays only in one of the clusters. This shows that a single discriminative vector has limited representation capability and fails to fit the manifold distribution, leading to the misclassification of the samples within the red box. Secondly, old classes exhibit significant changes in class manifolds and feature dispersion that lead to overlapped distributions. We can see Class 3 shows a transformation of its manifolds from the original spherical shape to a narrow elongated form in the updated model. These two limitations ultimately lead to the class-wise confusion problem. So the first challenge is how to capture the essential characteristics of classes, and the second challenge is to mitigate the effect of overlapped features on the dynamically changing model. Here we will demonstrate our proposed method. Considering real data often resides on a manifold structure within latent space, we construct an autoencoder for each class as manifold learners. Both encoders and decoders use a 1x1 convolutional layer with a hyperbolic tangent activation function. Then we utilize reconstruction error to measure the degree of consistency between the samples and the autoencoder subspace. We process the reconstruction errors to obtain the predicted probability of the sample, then minimize the reconstruction errors to 0 for samples on their ground truth autoencoders, and expect samples that do not belong to their specific classes to exhibit larger errors by the cross-entropy loss. Specifically, the autoencoder module is applied for each class to capture low-dimensional essential structures and implicitly encode the feature distribution into it, thus tackling the problem of insufficient representational capability. To mitigate forgetting of old classes, we apply the distillation loss on the logis level. We propose further class separation within the subspace to reduce confusion when disentangling overlapped features. Specifically, we introduce a confusion score which is transformed into adaptive weights for the constructive loss applied in class-specific spaces. Finally, the total loss function is composed of three components: cross-entropy loss, distillation loss, and confusion reduction loss. The complete algorithm for this model is written on the right. Experimental results demonstrate that our method achieves state-of-the-art performance in various scenarios. The visualized results highlight the superiority of the proposed method, which can learn a more separated manifold distribution for each class and reduce the overlap in the subspace. At the same time, our method achieves a better balance between stability and plasticity. We also conduct ablation studies to verify the effectiveness of each component. For more details, please refer to the full paper. Thanks for your watching.